So now we're going to look at the influence of the sun on our atmosphere, our climate and weather in a bit more detail. So we're going to look at what happens to that incoming solar radiation as it enters, passes through the atmosphere, hits the Earth, and then is re-radiated out. And we call that the Earth's heat flux. Flux just means change. So what are the changes, what changes occur to the incoming solar radiation as it goes through the path from the sun to the Earth and then back out again? First concept to understand is the difference between shortwave and long-wave radiation. Just simplifying the process for the moment, the energy that comes from the sun is shortwave radiation, and it finds it much easier. Shortwave radiation much more easily passes through the atmosphere. You'll see that some things happen to it, but most of it passes through the atmosphere. It then hits the Earth's surface, and as I mentioned before, the source of the heat of the troposphere is the heating up of the Earth, and then that re-radiates that out as long-wave radiation. And long-wave radiation is much more easily trapped by the gases in the atmosphere. Okay, so that's short-wave and long-wave radiation. Making it a little more complex again, if we look at short-wave and long-wave radiation, take this simple formula here. Q is the Earth's energy budget, okay? And it's in balance. It is zero. We know it's zero because if it wasn't, if it was positive, if the Earth's energy budget was positive, that would mean we would be gaining more energy than we would be losing, and we would be heating up constantly and would have heated up every year since the Earth was formed. If it was negative, it would mean the Earth would be getting colder and colder and colder. Now, it's doing neither of those things. Generally, on the whole, over a very long period of time, the Earth has a roughly stable temperature. Now, we might be changing that with the effect of climate change, but we'll just ignore that for the moment. So this formula here is just saying that Q, which is the Earth's energy budget, which is zero, is a balance between any incoming and outgoing shortwave radiation and any incoming and outgoing long-wave radiation. So it's not just as simple as the Earth's energy budget is only from the shortwave radiation from the sun and the long-wave radiation from the Earth. The atmosphere changes that incoming and outgoing radiation and does a whole lot of things to it, which we'll now look at in this animation. So let's have a look at what happens to the incoming solar radiation. This is the shortwave portion of the solar budget. Now we'll just start with 100 units of solar energy. The actual amount of solar energy that comes in is around 342 watts per metre squared, but we'll just simplify it and look at the budget by looking at 100 units. Okay, so the first thing that happens as that incoming solar radiation is that 3% is absorbed by the ozone layer. So we can say that that's an addition to our atmosphere. So 3 units, or 3%, is absorbed by the ozone layer, contributing to the temperature increase in the stratosphere. After that, 7% is lost to the atmosphere because it's reflected by the gases in the atmosphere. Okay, so 7% is reflected out just by the general gases in the atmosphere, and 21% is also reflected by the cloud layer of the Earth. So the water molecules of clouds, and they're white, so we know that the albedo is going to be quite high, reflects out 21% of that incoming solar radiation. We can also look at reflection from the Earth's surface, so it's albedo of the Earth's surface, particularly in snow-covered ice caps. So the Earth's surface itself also reflects some of that incoming solar radiation. That's the albedo of the Earth's surface. All right, now we can then say that this proportion of the incoming solar radiation, 31%, 21 plus 7 plus 3 is 31, is reflected back out to space. So we've lost 31 units from that incoming solar radiation. And what else happens? So what happens to the rest of that incoming solar radiation? Well, 3% is absorbed by the clouds. So they absorb some of that heat, some of that incoming solar radiation. Okay, so that's an addition to the atmosphere of the Earth. 18% is absorbed by the gases in the atmosphere and by dust particles. Okay, so that's an addition to the Earth's atmosphere. But you also have some of that radiation reaching the Earth's surface. Now, some of it will pass through the atmosphere and be reflected and scattered. Sure, 7% is reflected back out, but 20% of that incoming solar radiation that is scattered or reflected is also reflected down onto the Earth's surface and reaches the Earth's surface. So we can say 20 units reaches the Earth's surface via that scattering or reflecting effect, and then 25% will actually reach the Earth's surface directly. The shortwave radiation passes through all of those barriers and actually reaches the Earth's surface. So then we can say that by direct and diffuse processes, 45 units of energy reaches the Earth's surface. There's still other sources of energy that are being absorbed by the atmosphere and by clouds. So keep an eye on that too. So now let's have a look at what happens to that radiation that's been absorbed by the atmosphere or by the Earth. Remember, that radiation would then be re-radiated as long-wave radiation. So this is now the long-wave portion of the Earth's energy budget. So we've seen that 21 units have been absorbed by the atmosphere, and so that transfers as 21 units into long wave, and the 45 that's been absorbed by the Earth transfers as long wave. Okay, so that's 66 units. 45, 55, 65, 66 units. So remember, we're looking at the Earth's energy budget, and the balance needs to be zero. Eventually, energy that enters the atmosphere will be lost to space by long-wave radiation. So that 21 units of atmospheric heat input will eventually be lost, and the 45 units that was gained by the Earth will be lost to the atmosphere that will then be lost out to space by long-wave radiation. So let's just have a look at how that actually happens. So let's see what happens to those parts of the energy budget. So the Earth loses 19 units by evaporation. That's the energy that is used to evaporate water. We also lose 4% by convection, which is just the transfer of heat from the Earth into the atmosphere. Okay, so that's 4% just by convection. Okay, so as the air moves across it, it picks up some of the energy, the heat from the Earth, and moves into the atmosphere. We also then have this large cycle. This is essentially the greenhouse effect. It's the re-radiation of energy from the Earth that goes up into the atmosphere, and then there's also radiation back down from the atmosphere to the Earth. So the Earth loses 110 units, but also gains 96. Okay, so that's a cycle that occurs, and then you can see there that that greenhouse effect, the net effect is 14 units to the atmosphere, and the net effect of energy by evaporation and by convection is 23 units. And then we also lose heat directly out to space of 8 units. Okay, keep with me. Let's have a look then at the net effect of this long wave portion of the budget in relation to the whole energy budget of the Earth. Okay, so we've said if we add all of that up, so there's 66 units essentially net lost from the Earth's surface. All right, got that? And that is made up of 21 units of heat transfer from the atmosphere. There's 23 units from the Earth's surface through evaporation and convection, plus 14 units net effect of the cycling of the energy in the greenhouse effect, and 8 units lost to the atmosphere. Now that's 66 back out to away from the Earth's atmosphere system. 31% is lost even before it reaches the Earth's surface. So 66 plus 31 is 97. So we've missed 3% somewhere. And that 3% is the 3% that is absorbed by the ozone layer that is then just re-radiated directly back out to space. So the net effect in the ozone layer is 0, which is why it doesn't continually increase in temperature. So it absorbs 3, but also re-radiates that 3 out. And so there, if you add all of that, as in 69 eventually going back out to space, plus the 31 that was reflected directly back out to space, we equal 100 units. So the incoming 100 units is balanced by an outgoing 100 units as well. Hopefully that made some sense.